Nothing strikes fear into the hearts of computer programmers like the dreaded R word, recursion. You might even think that to use recursion, you have to be some sort of magician. Well, if that's you, Natasha and I are here to help. So how were you taught recursion? Well, you were probably told that it's when a function calls itself. If you were like me, you were then probably given some examples like factorial or Fibonacci numbers. Maybe even somebody held two mirrors up to each other and said, hey, there it is. So I think that's a hard way to start. What is recursion really? So in the context of computer programming, recursion is actually a control structure. So what's a control structure? That would be something like if or while that causes your program to jump somewhere else. And how do we learn control structures? By seeing what they do. So let's write a simple recursive program and let's see what it does. So I've opened up dev C++ here, and I've put in what must be the simplest possible recursive program. Let's take a look at it. All right, I have this function here called foo, and you can see that all it does is call itself. C++ requires a main, and you're not allowed to call the main. So I had to separate the main and have it call foo. And then foo starts calling itself. All right. So take a look at this program. Pause the video if you need to, but see if you can guess exactly what this program is going to do. So are you ready with your prediction? Well, let's run it and see. We have to compile it first, and it compiled successfully, so now let's run it. Okay, it says process exited after 2 seconds with return value, and there's a big number there. So did you think that this program was going to be stuck in an infinite loop and run forever? Well, that's not what happened. It only ran for a couple of seconds, and then it exited. And when dev++ says exited with this return value, that usually means that there's an error that happened. Well, I happen to know that that error number corresponds to Windows runtime stack overflowing. So to understand what just happened, we do need to know a little bit about how recursion works in a compiler. When a function calls another function, it has to remember where to continue running after that function is finished. So it has to save what's called the return address. Also, when it returns, it has to restore all of the local variables in the original function that's making the call. So all that information gets saved in a data structure and pushed onto the runtime stack. Well, in the case of our program, that function that was called then calls itself, and the process repeats, and then that function calls itself. And so every time it calls itself, it's pushing one of these data structures, which are called stack frames, onto the runtime stack. And that will continue until there's no more space in the runtime stack. And then it can't continue, and so it aborts. So that took 2 seconds this time for it to completely fill up the runtime stack. So it wasn't just sitting there in an infinite loop. It was doing something. It was actually generating the stack frames and feverishly pushing them onto the stack. And then it eventually stopped. So is there any way we can actually see this happening? Well, I've added a print statement to our program. So that our recursive function now, in addition to calling itself, it also prints out, hello, Natasha. So take a look at this program, pause the video if you need to, and see if you can predict what it will do when we run it. All right, here we go. You probably got this right. It's printing hello, Natasha over and over and over again as fast as it can. And it's printing it many, many times. So it just finished. It took 56 seconds and it eventually stopped. Again, overflowed the runtime stack. But it took a lot longer this time. Well, that's because the process of printing out hello, Natasha is extra work for the computer. And so it took almost a full minute before it overflowed the stack. Well, obviously, none of this is very useful because it's just running over and over again and then blowing the stack. So we need to get this recursive program under control so that instead of running many, many times, it runs for a certain number of times that we want it to run. So the simplest way I know to make our recursive program stop is by adding a parameter to the recursive function. So I've done that here. I have an integer parameter called n. Now when the main calls our recursive function, it has to send it an integer. And in this case, it sends it the number 1. And then when foo calls itself, it sends it with the original value of n plus 1. Okay? And there's an if statement in here that says it's only going to do that recursive function call if n is less than 5. So take a close look at this program and see if you can predict what it will do. You can pause the video if necessary. Okay, let's find out. Let's run it. All right, now take a look. It printed out hello, Natasha 5 times, and then it stopped. And this time it stopped with a return value of 0. And that means that no errors occurred. So it did not blow the runtime stack this time. Okay, let's see if we can make what's going on here even clearer by printing out the value of n. So in my print statement here, I'm not only going to print out hello, Natasha, I'm also going to print out the parameter n. Better add a space there to make sure that they aren't crowded together. We'll compile this and then run it. And now you can see it's saying hello, Natasha each time, but it's also printing n, and so you can see n is starting at 1 and counting up until it gets to 5. Okay, now we're going to do something really interesting with the code. Our print line here, I'm going to duplicate it after the if statement. And just so when this runs, we know exactly what we're looking at, I'm going to change this hello to goodbye. Now, this is a really important example. And so you should pause the video, study the code carefully, and try to predict exactly what it's going to do. And when you think you've got it, then resume the video and we'll see what this code does. Okay, you ready? Well, let's run it. All right, there it is. It said hello, Natasha 5 times, counting up 1, 2, 3, 4, 5. And then it said, goodbye, Natasha, also 5 times, but counting down 5, 4, 3, 2, 1. Now, understanding this example is pretty key to understanding what recursion does and being able to apply it yourself. Here, our recursive function foo was called 5 times, once from the main and from foo itself, recursively. Whenever it calls itself, it's in this if statement. Eventually, the fifth one doesn't satisfy the if statement, and so it doesn't call itself, and then it moves on down, continues on, and prints goodbye, Natasha. And that's the same iteration as the very last one, which was the fifth one. And then foo, that fifth iteration of foo, returns. It's done. But where does it return to? It returns to whoever called it, which was the fourth iteration of foo. So while the fifth iteration of foo was running, the fourth iteration of foo was sitting right here waiting for the fifth iteration to finish. And when that happens, then it gets to print its own goodbye, Natasha. So that's the fourth iteration. And then it returns back to the third iteration, which then prints goodbye, Natasha. So all the hellos print first, going in the forward direction, and all the goodbyes print after in the reverse direction. So look at exactly what happened. Our code looks like it has one loop in it with foo calling itself, but the effect was 2 loops. One loop that went in the forward direction and one loop that went in the backward direction. So remember back in the beginning of this video when I said you might think that to use recursion you have to be a magician? Well, this is like a magic trick. You get 2 loops for the price of 1. One loop in the forward direction for the code above the recursive call, and one loop in the backward direction for the code below the recursive call. There's one other little detail I'd like to point out, and it has to do with that if statement. There's a special name for it you may have heard called the base case. The base case refers to the condition under which you stop recursing. Very often in a computer program, the base case is expressed in an if statement, but with the reverse logic, showing that the condition under which you continue recursing. And that's how it's written here. We continue recursing if n is less than 5. Technically, the base case here is when n is greater than or equal to 5. That's the circumstance under which we stop recursing. And this particular if statement only says what to do if the if is true, but it doesn't actually specify anything to happen if the if condition is false, which is at the base case. So we can add that by adding an else. And so what we can do here is let's print out in the base case about a row of hyphens like that. So now we've added something for our code to actually do at the base case. Take a look at that, see if you can predict what it will do. And run. And now you can see that right at the base case where the recursion stops, we print that row of hyphens. And so that appeared in the else branch. It's also worth mentioning that you don't always need to use both of the loops. In our example, before we put the goodbye Natasha line in our code, we only had a forward loop. After we added the goodbye Natasha line, we had 2 loops, a forward loop and a backward loop. If we really only wanted a backward loop, then we could simply remove the first print outline, start with the recursive call, and then have the code that we want to run in a backward loop after the recursive call. So that's what I've done here. Let's watch that run. So in this example, we have only the backward loop. So to strengthen our understanding, let's take a look at an application, specifically a sleepy story. So this is one of the little golden book series for kids. And it was written in 1954 by Elizabeth Burroughs. Once there was a little girl. It was time to go to sleep, but she was not sleepy. Well, maybe she was just a tiny bit sleepy. She hopped into bed and covered herself up to her chin with her big red blanket. She said to her mother, "Tell me a story." So her mother said, "Once upon a time, there was a giraffe, a little giraffe with a long, long neck. It was time to go to sleep, but he was not sleepy. Well, maybe he was a tiny bit sleepy. He said to his mother, 'Tell me a story.'" I like how they have a palm tree as their house plant. So his mother said, "Once upon a time, there was a fox, a little red fox with a big bushy tail. It was time to go to sleep, and he was beginning to be very sleepy. He said to his mother, 'Tell me a story.'" So his mother said, "Once upon a time, there was an elephant, a little gray elephant with a big, big trunk. It was time to go to sleep, and she was beginning to be just a little bit sleepy. She said to her mother, 'Tell me a story.'" That furniture is made of big logs, very strong. So her mother said, "Once upon a time, there was a puppy, a fluffy black puppy with floppy ears. It was time to go to sleep, and she was a sleepy puppy. She said to her mother, 'Tell me a story.' So her mother said, "Once upon a time, there was a field mouse, a little gray field mouse with a long, skinny tail. She was a very sleepy little mouse. She said to her mother, 'Tell me a story.'" I like here how his bed is the matchbook, and they've turned the mousetrap into a sled. So her mother said, "Once upon a time, there was a pony, a little brown pony with a thick black mane." This, by the way, has my favorite picture. The little pony has taken off his horseshoes before going to bed. Anyhow, he was a sleepy, sleepy little pony. He yawned, then he said to his mother, "Tell me a story." So his mother said, "Once upon a time," but the little brown pony did not hear. He was fast asleep. So was the little gray field mouse with the long, skinny tail. So was the fluffy black puppy with the floppy ears. So was the little gray fox with the big bushy tail. So was the little gray elephant, the big, big trunk. So was the little giraffe with the long, long neck. And so was the little girl all cuddled up under her big red blanket, all fast asleep. Good night. Hopefully you noticed that the structure of the sleepy story was very similar to the structure of our recursive program. There were two loops through the animals. There was a forward loop where we were saying, once upon a time there's a little girl, once upon a time there's an elephant, and so on, once upon a time there's a horse. And then later we went through the same list of animals again in the backward direction, saying the horse was asleep, so was the fox, so was the dog, so was the little girl. So we had the once upon a time part of the story going in the forward direction, and we had the so was the part of the story going in the backward direction. There was also a base case. Did you notice what the base case was? It was when we got to the horse, and the horse was already asleep, so the mother did not tell the story. So what is the recursion? It's the story calling itself. Within each story, the mother is telling another story. So we should be able to actually write a little program with all the elements and generate it recursively. So let's see if we can do that. So let's first map this out in pseudocode. We have our story, shown here as a function called story, and it's going to be recursive. And it has a parameter, just like in our template, and that parameter is the animal, whichever animal the story is being told about. The first story is of the girl, so the initial call sets that parameter equal to girl. Then we have the forward direction of the story, which is the once upon a time, there was a whatever, and then so on. And then we have the backward part of the story, which is the so was the. And now Natasha is most interested in the base case, which is there in the center, that says, if the animal is awake, then we go on to tell the story about the next animal. What we do in the base case is recall what we did when it was the horse. The horse case had a unique line that said, but the pony was fast asleep, did not hear. And that was unique to the pony. So that is shown in the else, just like we did in our template. Well, what about all those other little details? Like the giraffe had a long neck, the elephant had a big trunk. Well, we could try putting all of that in an array, or maybe parallel arrays. Now, this is a great exercise to do on your own, and I strongly encourage you to do so. If you'd like to look at my solution, I have a simplified version here. Let's take a look at it. Since all the data are strings, I had to include a string library. I have 3 parallel arrays, one for the animals, one for their details, like the little girl had a blanket, the giraffe had a long neck, and so on. And then the third array, how sleepy they each are. Now, the recursive function is called story, and it has an integer parameter that will serve as an index into those arrays. And the main starts by sending a 0 to that story, so that the first story will be about the girl with her blanket who is awake. Then if we look in the meat of the program, which is the story recursive function, we'll see that there's some printout statements which print out the first part of the story that starts once upon a time there was for each of the animals. And you can see that that portion makes reference to each of the 3 arrays to look up the data to insert into the story. Then we have the test for the base case. And just like in our template, it uses reverse logic. So although our base case was when the animal was asleep, namely the horse, the test we're doing is if it's not asleep. And so if the animal is not asleep, then it recurses and tells the next story. And thus the call to story of A plus 1. A is the parameter. And just like our template, the else is what to do specifically in the base case, which in the case of the sleepy story was we mentioned that the pony was fast asleep. So that's what happens here. And then there's one extra detail here, and that doesn't exactly match the template, And that is that in that case, we return without doing the reverse part. And that's because we never said, so was the pony. The story just went straight to the next animal. So we want to avoid saying, so the pony was asleep, so was the pony. So thus we've inserted a return statement here. Then the code that's after the recursive call is the code that will execute in the reverse direction, which was the latter part of the book where we were saying, so was the elephant, so was the giraffe, so was the little girl. And so that's shown here. Let's run it. All right, so here's our abbreviated version of the sleepy story. Of course, there's many details that haven't been included, like there are different genders for some of the animals. There were some additional details. But the whole structure is there with a little extra work, maybe a couple of extra parallel arrays. You can match the story pretty much exactly. And there's more. In our example, we chose to implement the sleepy story with parallel arrays. But what if instead we had chose to use a linked list, such as pictured here, where we have a record for the girl and her properties and a pointer to the next animal, in this case the giraffe, and so on, where we have a forward linked list. How would that change the way our program would be laid out? Well, the if statement would look different. Of course, the printouts would look different because we would be referencing records rather than array elements. But the if statement would look, for example, something like this. Instead of making reference to the sleepiness by looking it up in an array, we would be looking at the sleepiness field of the animal. And instead of recursively calling with an index +1, we would be recursing on the next animal. So if the animal was parameter A rather than an index A, then we would say that animal dot next. So if you're familiar with linked lists and pointers, you could see this is how you would make the change to implement it that way. But now suppose we did that. We only have forward links through our linked list. What about that backward portion of the story where it says, so was the mouse, so was the dog, all the way backwards to the girl? We don't have, in this picture and in the scenario I just described, we don't have backward links. If we only have forward links, will our program still work? Will it be able to do that backward direction of the story? And it turns out that we don't need backward links, that we can set up a simple forward direction linked list like this and simply change the references in our story, and both the forward traversal and the backward traversal will function the same. And the reason for that is because each time we move to the next story, recall that the local variables are saved in the stack frame. So that means that while the elephant story is being told, the information about the giraffe is sitting in the runtime stack. And when the elephant story is done and we return to the giraffe story, those variables are restored. And so we don't need the backward links to traverse that list backwards if we use recursion in this manner. And there's our second magic trick. You can traverse a linked list backwards without back links. If, for instance, all you wanted to do was traverse a linked list backwards, then you could start with a recursive call to the next element, and then all the processing that you wanted to do on the list going backwards, you would place that below the recursive call. And the traversal backwards is handled for you by the runtime stack. Now, since you're all becoming magicians with recursion, we'll leave you here with what is possibly the most spectacular of all of the magic tricks in this video. And that is, let's take a look back at our Sleepy Story program that we wrote. I claim that this program has no variables in it. That's right, no variables. You're probably looking at this and saying, wait a minute, aren't these arrays variables? And what about this int here? And I'll claim those are not variables, those are constants. What's a constant? A constant is an identifier that we set to a value and then never change the value. Well, that's exactly what's happening here. And in fact, we can specify identifiers to be constants in C++. And let's do that right now. Let's add the notation that each of these arrays is actually a constant. We'll see if the program still works. Now wait, you're wondering, what about this int right here? Is that a variable or is that a constant too? Because it takes on different values over the course of the program running. However, remember that each invocation of the story has its own value for A, and once that's set for that function, it doesn't change. It only changes for the next invocation. So it turns out we can put const here too. And you may be wondering, well, wait a minute, what about this a plus 1? Isn't that changing the value of A? And it's not. A plus 1 is not an assignment statement. A plus 1 is an expression. It's simply computing a value. And then it's sending that value to a different variable A in a different instantiation of the story function. So I've replaced all of the variable declarations in here with const flags in front of them. And so now let's see if our program still runs. So we'll compile it and then run. And here's the output, same as before, only this time our program doesn't have any variables in it. So did you ever imagine that you could traverse a forwardly only linked list, traverse it backwards without even using any variables? So that's a magic trick indeed. And now for those of you out there who are starting to feel like grand wizards of recursion, I have one little extra for experts example to show you. And it has to do with this very first example program that we saw. Remember this one? Super simple, just the main calling a function that calls itself, and that's it. Now, if you remember, when we ran that program, what happened was it crashed after just a couple of seconds by overflowing the stack. Interestingly enough, some of you out there may have tried to run this program and it didn't blow the stack. Instead, it ran forever. Well, that's true. In some compilers, this program actually will run forever and won't overflow the stack. Why? Well, it has to do with how optimized the compiler is. This particular program has a property called tail recursion. Tail recursion is where you have a recursive function, and the very last thing the function does is the recursive call. And that's the case here. It so happens it's also the first thing the function does, is the recursive call, but it's also the last thing that the function foo does. When you have a situation like this where there's tail recursion, a compiler may detect that and replace the recursion with a loop. Now, my def++ compiler by default does not perform that optimization. But if I turn on its optimizer to its maximum level, it will do it. So I'm going to go under compiler options and add the option -optimize at level 3, which is the highest level in this compiler. And now I'm going to recompile and rerun. And this time, the program does not crash. It does not overflow the stack. It really is running forever. By the way, the author of the Sleepy Story, Elizabeth Burroughs, wrote that book in 1954, long before any computer system supported recursion. I had the opportunity to interview her grandson, who described her as a very creative, forward-thinking person who was fascinated by the sciences and by math. And she lived in Stockton, California. And in fact, her son became an early computer scientist in the late 50s, early 60s. Well, I hope my video has made you less afraid of recursion and has inspired you to give it a try yourself in your own projects.